a voltage maximum is located at 0.079 lambda away from the load.
0.79 lambda away.
Away. And then it says determine the load.
Right. Now, first of all, did you all see the solutions too? Can you see them okay?
I think there's another zero, it's 0.079.
0.07.
Yeah, 0.79.
All right. All right, so but y'all can see them, right? Y'all render? Okay. So for this one, shut up that projector. I'm gonna just sketch a Smith chart here. If you don't understand it, get a fresh Smith chart out here and work this with me. All right. So this is my Smith chart. All right, and here's the one circle. It's R equals 1. And so now we have something where it has a VSR of 3.4. So take your compass and go ahead from this point. You're going to come out, you're going to see that a thing that's about 3.4 right here. This is going to be a circle of 3.4, all right? From here to here, take it and make a circle. Like that. Now the reason I say this is I know when you go ahead and plot Z load normalized, so wherever it is here, and you're going to go ahead and move, the Vmax occurs here, and it's the intersection between this 0 point and the infinity point here, where it intersects there is greater than 1. So you're going to see something of 3.4, and that is your VSWR. You follow me on that, class? Everybody got that? We covered that last time. So now we know the radius of the circle, that's the bottom line. The radius of this magnitude of reflection coefficient. Next, he says that the maximum occurs 0.079 from the load, right? Now think about this. When I move here, if I move here, if I'm moving in this direction, I'm moving wavelengths towards generator, right? So that would be in the direction that, if I think about this, it's 0.079 lambda from, it says the load, right? The maximum occurs. That means if I see this as 0.25 lambda, it doesn't matter which scale you use. Do you all see that right there? If I subtract 0.079, what do I get? 0.25 minus 0.079. Tell me what that number is, lambda.
0.171.
0.171 lambda, right? Now this is wavelengths towards generator I'm using, all right? I'm using the outer scale on purpose. So if I take a look at that, I'm gonna see this is going to be is that about where it is right there? Right?
Yeah.
All right, now what you do is go ahead and draw a straight line through there, and this point is gonna be ZL. That's the load, because if you think about it, if you went ahead and came in, normalized your load, it would be there, right? And then if you move 0.079 lambda, it would be Vmax. Do y'all follow me on that? Now, what else is the question asking for? What is the load or what?
Determine the load.
All right. Well, can somebody just look here and tell me what ZL is right there? The normalized value of ZL? Can you see it? Do it on your Smith charts, because it's important that you get, the more you work with them, the better you remember how to work with them. What did you get?
Is it roughly like it's 1 plus J 1.3? Roughly.
Is anybody else getting that before?
Yeah.
1 plus, say it again?
J 1.3.
1.3, so it's right on the one circle, right? That means the actual value of ZL would be Z naught times small ZL, which is going to be 50 plus J what?
65.
That's about right. Ohms. Is that the answer?
Yeah.
No, the answer was wrong.
The answer's wrong.
Well, so on that, when you did 0.25 minus 0.079 lambda on the answer, there wasn't a 0.171, it was just 0.071 throughout the answer.
Oh, they subtracted wrong?
Mm-hmm.
That would be way over here.
That's what it is in the solution.
Okay, so it's the wrong answer, but this is how it should be. Everybody follow me there?
How did we know how to subtract or not?
Well, You could use the other scale. I'm using the outer scale because that's the one we always use. So if you think about it, if you come in here, right, you're at the load. When you move this way, it's wavelengths towards generator, right? They said the maximum was 0.079 from the load. So what we need is this arc distance to be 0.079 lambda, right? This is 0.025 lambda, that's the mile marker, so we subtract 0.079 lambda from it, and we come here. That's 0.171 lambda. All right. Does everybody understand that? Any other questions about the homework? There were some good problems there. Nothing else? You got me anything, Josh? No?
I mean, I didn't understand the second half of it, but I
What,
don't think we covered
which
it.
problem?
The,
Oh, like the coaxial cables and whatnot.
Just tell me, this is probably measuring Vmax on a coax. There's a thing called a slotted line that they use, and you can actually take a look at the voltage between the inner core and the outer shield on a coax with this little thing that you move up and down. It's got to be a split line to do this though, but it's an experiment more than anything. Which one is it?
let me find it.
Here you go.
2.31.
Alright.
So it shows a Smith chart and it's generated on a 50 ohm slotted coax cable.
All right, let me get this Smith chart up here, we'll talk about it. Not a very good one, but, so this is 0.25 lambda, and this is 0, and go ahead.
A is at 0.5.
Let me draw a coax cable, and I'm gonna put a load here.
No, on the Smith chart.
And, now go, is this 0 point?
It's not showing a diagram. It's on the Smith chart.
Okay.
There's a point A at 0.5 and 0J.
0.5, that would be out here, right? And 0J, that would be right here.
Yes.
All right, so that's A. Go
And
ahead.
then there's a point B, slightly below on the same circle at 0.351 lambda.
Below it,
Yeah, below it.
point B, and that has, this mile marker is what?
0.351
From the generator or from the load?
toward generator. So,
All right, well, oh, that's 0, right?
yes,
Go all the way right here, that's 0.25. These numbers are between 0.25 and 0.5, aren't they?
yeah, is 0.35.
Oh, I'm sorry, I didn't hear you. 0.35, go ahead. 1 lambda?
Yes.
Okay.
And then, this coax cable is terminated in a short circuit
Okay.
and then in an unknown load.
Okay, but the short circuit is what? I mean, what I'm not seeing is, can somebody just read the problem entirely? Go ahead. All right, it says a 50 ohm slotted coaxial air line is terminated in a short and then in an unknown load. Determine A, the measurement frequency, B, the VSWR when the load is attached, and C, the load impedance. Oh, so B is not on that circle, it's on a different circle. See, there's a different radius. Here's the radius and then this goes like this, right? Take a look at that. And there's B here, right? Isn't that what it
Yes.
says? All right, now, and it says,
I think you're looking at the wrong figure.
I am,
You're supposed to look at the one in the book.
figure 2.56. Let me just take a look. Yeah, you're supposed to look at figure 2.56 in the textbook. So the loads, let me tell you how you get this. Do you see, does everybody see this figure in your textbooks? Right here, that's where it's from. That Smith chart business, we'll get to in a second.
What page is that?
This is page 110. And he shows you the one where you have, let me just go through this. What he has is a voltage measurement, and then he has a 0 out here. And when it's a short circuit, it actually looks like this. He has something that looks like. All right, do you see this right here? Now, when it's a short circuit, the VSWR is infinite. All right, let me just show you this. VSWR, VSWR, is equal to, if you think about it, what is it? It's 1 plus the magnitude of the reflection coefficient over 1 minus the magnitude of the reflection coefficient of the load, right? Well, what is the magnitude of the reflection coefficient if it's a short? If it's a short circuit, it's what? It's ZL is 0 minus Z naught, right? Over 0 plus Z naught. That's minus 1, correct, class? All right, what's 1 plus the magnitude of minus 1 is 2, right? Over 1 minus the magnitude of minus 1 is 0, or this is infinite. So a short circuit has an infinite VSWR, and that should be something he's trying to indicate there. It's just I can't tell for sure. Oh, he's just showing you the voltage. The actual VSWR will be infinite because take a look at this. This is the magnitude of the voltage on the line. You see how this is the 0 point here, class? Now, when you have a short circuit, what happens on the line, the voltage magnitudes peak will double the actual input voltage. If you input a generator voltage of say 5 volts, your peak here will be 10. Are you with me? So whatever the voltage is you put in, you'll get 2 times the magnitude of V naught, or Vn, call it Vn right here. But this is still 0, so the ratio, when you look at the VSWR, it's magnitude of V max, right, over magnitude of V min. Well, since V min is 0, this is infinite. So that's right, you follow me? So this is what you're looking at when he has the short, but you'll notice something. That short circuit gives me 1 point that's very important. It shows me where the load is. Here's 0, the load is close to 0, but remember, it's not an exact scale. If you read the book, he talked a little bit about this. This is an experiment where you don't know exactly where it is, but you know how to find it. If you short the load, right? Or you replace the load with a dead short, then you know where the loads should be, right? I mean, where it will be. And that's where the actual load is. This is where the load is. Are you with me, class? You follow me on that? This is just a random scale he put in there. Normally, you put the load at 0, but this time it's not at 0. How do we find where it is? We put a dead short on there, and now we know where the point is where the load will be attached. Are you with me, everyone? And I don't know that distance. Can you tell me what it is?
So 1.25 centimeters.
Is it 1.2? So this means that this distance from here to here is 0.25 centimeters, or this is at Z.
1.25. Sorry.
Oh, I'm sorry, it's minus 1.25 centimeters right here, right? Correct? Now what does he do? Oh, by the way, here's how we get the wavelength. Is the velocity c on there?
It doesn't say.
Then we have to assume that the velocity on the transmission line, like here, where this is ZL, and this is Z naught. If it doesn't say different, or unless there's a better reason for it, then you have to assume, I don't even know what that is. Is it 50 ohms for this one or 100?
50.
50? All right, you have to assume phase velocity is going to be C. Now, here's the thing. Listen, once you short this, what you have is, you know something. You know from minimum to maximum, if you think of a Smith chart, that's where V max occurs, right? If you go around a quarter wavelength, that's where V min occurs, right? You go back, V max. How far did I travel all the way around? 1/2 wavelength, right? That means this distance from here to here is just lambda over 2. Are you with me? So can you tell me what the distance is from here to here? Off that graph? This is a good problem. Everybody follow me on this? You look for the dead short to get the wavelength.
The distance from is like 6.3 centimeters.
Anybody else confirm that? Now, I don't know if you can read that chart. If that's 6.3 centimeters, lambda is equal to 12.6 centimeters, right? Agreed? How do I get the frequency now?
C over lambda.
I know that lambda is equal to C over F for a lossless case, and that means F is equal to C over lambda. And that's 3 times 10 to the 8th meters per second divided by 12.6 times 10 to the minus 2 meters. And what do you get for that?
2.4 gigahertz.
2.4 gigahertz. Dr. Wentworth probably chose that because that's a Wi-Fi frequency. All right, you with me on this one, class? Now, what's the next part of this? Yes, so we got the frequency.
The VSWR when the load is attached.
And that's from the graph, right?
Yeah.
All right. Well, if you look at that graph, and I'm going to put it right here. I'll redraw that in a second. It has, well, it has that, but then it has something that does this. I'm not even sure if it, quick look at that. It's this one, right?
Yes.
So it does sort of this. Are you with me? Now, you can take a look at the max, Vmax here, and this is Vmin, right? So your Viswar with the load attached, what's the maximum voltage? Can you read it off? What is it? 4. And what's the minimum?
2.
So that means we have a Viswar of simply 2, right? Correct? Well, then that sort of tells me everything I need to know, because now when I go to a Smith chart, and I have a Viswar of 2, that means I know the radius of the circle. And that's going to be right here at 2. Actually, it's a little closer, it's about here. So this is going to be 2, and that means this is what your circle should be. Redraw that a little. It's probably more like this. And this will be, this is a Viswar of 2 right there, right? Now he asks, what else?
The load impedance.
The load impedance. So, this is Vmin here, right? I'm going to try to do this right. If that's V, I mean, this gives me the position of the load, correct, class? And then when I replace that, I'm going to replace the short with the load. This is something I gotta. All right. The load is right here. This is going to be. Let me just look at that drawing exactly. Sorry. It looks like it hits a minimum at 2. Is that where it is about? It's hard for me to tell exactly.
It's closer to 1.9.
Right here, 1.9. Boy, I wish that was blown up. So when it's a short, let me explain something. When it's a short circuit, and you came in and normalized the load of a short is 0 ohms, right? When you normalize it, you have 0, correct? The point that represents 0 is this point right here. This is 0. That means you would think that you would come here and you would draw your circle, which is just the outermost part of that circle, right? Now that's what would happen. I mean, that's where it would be. I'm trying to say this correctly. if it was a short circuit, that's, you basically would come in here to this point. Now, we know we have this circle right here. So that means this point corresponds to the V min right here. This is gonna be V min, and that would be V max here. Now, I'm trying to see what I'm trying to do is get the difference in length between the point where the actual, that, whatever that is 1 point, you said 2.5, minus 1.25? What's the difference between that and the point where that 1.9 is in centimeters? I'll show you what I'm after. I want to find this distance right here from the actual V-min with the load and this point. Can you tell me that distance? And we'll get this thing. If you just give that
0.65.
0.065, did you say?
0.65.
65 centimeters, is that right? All right, now, we have to take that and turn it into wavelengths. Are you with me? So, when I take a look at that, the actual delta lambda would be equal to 0.65 divided by, and the wavelength on this is going to be equal to 12.6 centimeters, so it would be 0.126. Wait, is that 0.65 centimeters?
Yes.
Oh, I'm sorry. Then it's going to be 12.6. And what do you get for that? 0.65 over 12.6?
0.0515.
0.0515 lambda. All right. Now, here's the deal. With this particular one, I know that when I attach the load, the voltage minimum is away from where the load is. Do you follow me? It's towards the generator, so follow me on this. I know this is the circle I'm operating on with the load. That I know from the visual, right? But I also know that that's where the actual V-min will occur, right? But it doesn't occur there. I mean, excuse me, when I take a look at this, I see that the distance I have to go to get there is this distance. This has to be a distance of 0.0515 lambda. This has to be 0.0515 lambda. So here's one way to get it. You can say that's 0 right there, or you can say it's equal to 0.5. If it's 0.5, if you subtract 0.0515 from it, what do you get for this mile marker? Do you see what I'm doing here?
What's your question?
Here's the deal. This point to this point right here has to be equal to this distance. It has to be the wavelengths, the actual fractions of the wavelength. We found the actual distance between the minimum where the short circuit was, the 0 voltage, and the minimum voltage once we attach the load, right? Now what I need is this point in terms of wavelengths towards generator. So if you think about that, 0, 0.25, then it's 0.5. Start with 0.5 and subtract 0.0515 from it. What do you get for that mile marker? 0.4485. And I'm going to tell you one thing, Lambda. The whole thing about this is based on the eyeballs. We're estimating. We don't have an exact values here. So there's going to be slop, there's going to be error. Now, that means this point is the load, right? So I think you said that was A and this is B, and what he's showing, is that right? All right, now, can you give me the point there, the values?
0.55.
0.55 minus J what?
2.5.
0.25. 0.25, is that right? Minus J 0.25. So that would be your normalized ZL. Are you with me, class? Does that jive with you? You getting about that? How do I get ZL now if I get normalized ZL?
Multiply by Z0.
Multiplied by Z0, and Z0 was 50 in this one, correct?
It was.
So if you multiply that by 50, what do you get for ZL? Just tell me. 0.27, something like that? plus J,
27.5.
all right, I'm sorry, 27.5 minus J,
12.5.
12.5. Is that what he has, something close to that? What does he have?
28 minus 12.
All right, now this one is kind of based on reading that graph, and that's a tough one to read for me. So there's going to be a lot of slop in this one. If he'd blown that figure up and like located the actual minimums, it would be a lot easier for me to do that. But that's what he's talking about. Does that answer your question? The whole idea is this: the minute you have the Viswar, the minute you have that, you have the radius of that circle. After that, if you put a short circuit in, we know the short circuit is going to occur right here, right? So at that point, we locate the load right there. And then from there, you can take a look at that graph and you'll notice as we move from the load point towards the generator, we hit the V min, right? So here's the low point. As we're moving wavelengths towards generator, we go through that point, wouldn't we, class? Are you following me on this one, guys? All right. All right. Another question? These are good problems, by the way. They make you think. Any other ones?
2.35.
Okay. Which one? What does this one say?
A matching network using a reactive element in series with.
Which brings me to my next topic today is matching. So we're going to do this. We're going to do this. If you did it, great. If you did the reading, so I'm going to show you how to do impedance matching. I'm going to show you something about, before you read the problem, I'm going to explain to you what's going to happen. All right, what we want, when we deal with transmission lines, as engineers, we want no reflections. We want a Viswar of 1. We want a reflection coefficient of 0. That means all the power gets transmitted to the load. Do you follow me on this? You don't want anything reflected back. That's bad. And I'll tell you a story very quickly. When I was doing some work for NASA years ago, I had to design an antenna, and this is with software I was using, and the antenna was going to be connected to, I believe it was 50 ohm cable, which made my input impedance to the antenna had to be 50 ohms for a match, right? Well, after we designed the antenna, so the technicians fabricated it, and I wasn't there for this. And then they sent, I think it was, actually I'm not sure who fabricated this one. I wish I knew. So then what happened is, this gets sent out to Ball Aerospace. This is a big aerospace group out in, I think in California, but somewhere out that way. And they did the measurements. And the person who was doing the measurements, thank God, was an engineer, electrical engineer. He wasn't just a tech. And they said, your Viswar is 4. I mean, when you hear that about an antenna you design, this is not a little bit of slop. This is a major foul up. That means it's a horrible match. So he went back, and thank God he inspected it. And one of these guys who did the soldering put a big fat solder ball on one of the leads that connects to the coax. Now what that does is introduce a large inductance by accident. And what he had done is, instead of having a match system where all the wires were short and they were soldered perfectly and stuff, we had a very unmatched system. So he went in with a soldering gun, cleaned it up, and connected it back. And the Viswar then was about 1.2, something like that, which is acceptable, and the antenna worked. But that's my story on why Viswar is very, very important, because that antenna wouldn't work at all with that Viswar of 4. Now, getting back to this thing, when we do matching, that's the way we get rid of problems that would be impedance mismatching. Like you get a load of 100 plus J60 and you got 50 ohm cable, that means you're gonna have a lot of reflections. So how do you get rid of the fact that you're gonna get a lot of reflections? You do impedance matching. And here in a nutshell is what it is. Usually when we have, just write this down, or you can listen. You don't have to actually draw this. When we have ZL and Z0, I put it at 0 here, and this is positive Z. We know for a fact that the reflection coefficient on this is going to be ZL minus Z0 over ZL plus Z0. We know that. Well, that's bad. If we have anything but ZL equaling Z naught, it's bad, right? So how do we get rid of this problem? Well, here's the Smith chart, my little drawing of the Smith chart. Oops. And that's the R equal 1 circle. So if we come in and we plot ZL here, let's say this is my ZL normalized, and I'm going to draw this like this. That's ZL, this is the reflection coefficient's magnitude, that's the radius of that circle. When we move from this point, whatever it is, point A, to this point, where this circle intercepts the 1 circle, that's the R equals 1 circle, I move a certain distance. And I'm going to call this right now just L1. So I'm going to move from here down to the point, a distance L1. So I'm moving wavelengths towards generator that distance, all right? Now, this is important. Right here, my value of impedance at that point, normalized impedance, mind you, ZL normalized, remember, is going to be capital ZL over Z naught. Well, now the normalized impedance right here is going to be 1 plus JX. It's got some other value, right? Everybody hear me on this one. Now, JX is a reactance. We could also move to this point right here. This would be 1 minus JX. It would be the same value of JX. That would be negative, right? All right, now, hear me. If I move to this point and I have 1 plus JX right here, what if I go ahead and I put an element in here, say a capacitor, that would have a normalized impedance of minus JX? Well, what happens? It's in series, right? 1 plus JX minus JX is just 1, right? Now, what would the normalized impedance be then, looking at this point? If right at this point, I'm assuming it's a distance L away. Well, the normalized impedance, that would be Zn at this point, would be equal to just 1, right? And that means the actual impedance, Zn, or capital Zn right here, would be Z naught, right? Which means the reflection coefficient would be 0. Isn't that right? Then Z naught, then the input impedance would be the characteristic impedance of the line. Does everybody follow me on this? So let's go ahead and talk about this. Let me give you some real numbers. Better yet, we'll do it theoretically. So if I'm right here, and I want the normalized impedance of that capacitor to be minus JX, well, the actual impedance of the capacitor is what? Minus 1 over, or really it's just what? Normally the way you were showing it was 1 over J omega C, correct, class? Well, that can also be written as minus J over omega C. Agreed? Now that's not normalized impedance yet. That's the impedance, correct? To normalize it, we would divide this by Z naught. And then we would say, whatever this value of JX is there, I would say that the capacitive reactance would be 1 over J, well, 1 over, it would be minus J over omega C Z naught would be equal to the actual minus JX that I needed, which means that the value of C right here would be, C would be equal to 1 over omega Z naught X. Do you follow me on this, class? Are you with me? And that would do it. Now, getting back to the problem that he's talking about, is it 32 or 31? 35. What? Is it 35? So this is going to be problem 2.35. Give me the specifics on this one.
A matching network using a reactive element in series with the length D of T line is used to match a 35 minus J 50 ohm load to a 100 ohm.
So ZL is equal to 35, go ahead and say minus J
50
and Z naught?
to a 100 ohm T line at 1 gigahertz.
1 gigahertz. That's important for the value of the capacitor. They want the elements value, right?
and find the through line length D
Mhm.
and the value of the reactive element. If A series capacitor is used, and B, a series inductor is
All right,
used.
we're gonna do this problem. So let me redraw the Smith chart. Get a fresh Smith chart out. This is a good problem. I really like this one. Because this shows you one way to do matching. All right, for this problem, get a Smith chart. And first, I need to take and normalize the load. So if I have ZL over Z naught, what do I get? That would be small ZL. Can you tell me? Point what? 0.35 minus J, 0.5. So now I gotta locate that. Well, if this is the R=1 circle, I like to draw that first. I know the 0.35 circle is about here, right? That would be R equals 0.35. And then the minus J.5 would be down here. This is minus J1, so this is about minus J0.5. And so what you find is this is the point right here where they're going to intersect. And this is ZL, or 0.1. Can you all find that on yours? Remember, it's down here in the lower hemisphere because that minus J, right?
Yeah.
With me? Remember, it's down here. Okay? It's minus J, isn't it? Minus J.5. All right, that's 0.1. And now take that and go ahead and do the old, use your compass and make a circle with that radius. Not a very good circle, but nevertheless a circle. Got it?
What is that dash line that you have?
I'm just trying to show you, this is 0.35, an estimate, and this is gonna be,
Oh, okay,
that's an
okay.
estimate of minus J.5. You guys got that? And let's get the circle. Now, look, I wanna show you. From here, you gotta get the mile marker here. You gotta get wavelengths towards generator, that marker. What is that point on this one?
About 0.42.
Check that out. Is it 0.42 lambda? And that would be at the load, right there. About 0.42, guys?
Yeah.
You guys getting it? Everybody see this now? You see it? You want one? I think I might be able to spare one. Yeah, because you're gonna need a little quiz today anyway. All right, now, hear me. We need to go to one of 2 points, either this point right here, or this point. Why? Because at that point, I have one, either plus or minus J something, correct?
Yeah.
So we're gonna go to this point first. I call that 1, I'm gonna call this point 2. So now I have to move from here, and how far do I have to move? Well, draw a straight line through this point from the origin right here. And you're gonna see a mile marker here, and that wavelengths towards generator, what's that value? You gotta go right where that circle that you just, the circle of constant reflection coefficient, where that intersects the one circle. What do you get? For the mile marker?
Sorry, 0.173.
Anybody confirm that? About one? All right, so this is 0.173 lambda, right? Now, what that tells me is this. When I have my load right here, and this is the Smith chart, or I mean, sorry, this is the transmission line. He calls this the distance, the through line. So he'll call it, I think, D through. All right, that's that distance. So how far do we have to go? Please watch this, because this one can be a little tricky. This is the point I went to, right? So I take that value, so it's 0.173, and I subtract this value from it, which is 0.425, right? Now what do you notice about that when you do the subtraction? What do you get? Anyone? What's that value? Minus what? 173 minus 425.
0.252.
0.252 lambda, right? Now, you see it's negative, right? You always take the point you arrived at minus the point you came. If it's negative, anybody have a suggestion? What do we do? Add a half wavelength. That's right, we just add 0.5. So then we add 0.5 to this, right, lambda. And what do you get?
0.248.
Lambda, right? So that's this length here. You have to move from this point to this point, which is just about a half wavelength. So this D through is 0.248 lambda. If it was 0.25 or an exact quarter wave, that would be a right answer too. He probably wanted a quarter wave. Are you with me? You follow me on this, Duncan?
No.
All right, look, this is the point we started at. Do you agree with that?
Yeah.
This is the point we want to go to, right?
How did we find the point we want to go to?
Because it's 1 plus something. This is going to have 1 plus jx. This is 1 minus jx, right?
Oh, okay.
Right? And we want to go to that point, the value where the real part is 1. So you want to intersect the 1 circle. And the reason we want to intersect it because we can get rid of that j term by adding an element. And then we'll have then the input impedance will be just Z naught. Do you follow me on this? All right, now work with me on this one. So that distance is there. Now, you've got to do this too. When I look at this point, I know the real value is 1, but what is the imaginary value? It's 1 plus j what? Take a look at that. They're going to be something like this. What is it? Can you confirm that? This is j what, 1.4?
1.4.
All right, so it's j 1.4, and that's normalized, right?
Yeah.
All right, there's a couple ways to do this. I like to do it this way. Well, if it's plus j, I want to add an element that would have a minus j sense or a capacitor. Do you agree with me? Capacitive reactances or minus j over omega c. So now I take this value, and I want to add a minus j 1.4 here. That's what I want, right? And that's going to be a capacitor. I want to put that value in line. So then my normalized input impedance here, Zn, would be equal to 1. So I say j 1.4 would be equal to, or minus j 1.4 would be equal to minus j over omega c times Z naught. Again, I've taken the capacitive reactance, 1 over j omega c, and I normalized it, or I divided by Z naught. Follow me, guys? Which means now I have 1.4 equal to 1 over omega c Z naught. We can get omega because he gave us the frequency of operation as a gigahertz, can't he? Right? And he gave us Z naught as, what is Z naught? Is this 50? Or is it 100, right? So now I can say that my value of the capacitor would be 1 over 1.4 times omega, which is 2 pi times 10 to the 9th, because it's 1 gigahertz, times Z naught, which is 100. And now you can tell me the value of the capacitor, which is very, very small. Y'all see what I've done there? Remember, the whole deal is, once I have that 1.4, J 1.4, I have to add something in series to get rid of it. And what am I gonna add? I'm gonna add a minus J 1.4, which boils down to a capacitor. And the value of that capacitor, normal capacitor reactance is just 1 over J omega C. Since we're normalized, we're talking about normalized impedance, I have to divide that by Z naught. Do you agree with me, everyone? So what is this capacitor value? Anybody?
0.714 times 10 to the negative 12.
0. Go ahead, say it again.
0.714.
Picofarads. All right, now what does he have in his book for that capacitor value? The solution. No, I mean, it should be in there. You see it?
Yeah, 1.14.
For the capacitor?
Yeah.
Yeah, that's what I got.
Oh, that's what you got when you did this calculation?
1.14 picofarad.
All right, I think 1.14 picofarad, right? Isn't that right?
Yes.
1.14 picofarad, and that's what he has? I think you made a calculation error. Remember, frequency is 2 pi f.
Yeah, we looked at the second time.
It came out right?
Yeah.
This is another thing I'm gonna stress. When you're doing calculations, do the redundancy check, run them twice. Because a lot of times you get fat fingers and you hit the wrong key. I'm telling you, I've learned this lesson the hard way. All right, now that's if I'm using a capacitor, right? Let's take part 2 of this problem. Now I come down here, here's my ZL, here's my Z naught, but now I want a Z through, this is gonna be D through, but 2. Now what I'm gonna do is I'm not gonna just move to this point, I'm gonna go from here, I'm gonna go all the way around, but I'm not gonna hit the 1 plus J, I'm gonna hit this 1 minus J. So I'm gonna keep going, and I'm gonna come to this point right here. And this is gonna be the 1 minus J, JX. So give me the mile marker here if you can. On the wavelengths towards generator.
326.
Is it 0.326? Is that right, guys?
Yeah.
You guys get it? You might get slightly different, like it might be 0.31, 0.33. Depends how sharp the pencil is and how accurate your drawing is. You see?
I got 326.
326, okay? So now we're there, right? Now we have to calculate this distance from here all the way around. We know if we go all the way around to here, we get half a wavelength, right? So now I take always the point you ended up at, which in my case is going to be 0.326 lambda, and we subtract from it the point we started, which is 0.425, right? And that gives me what? About 0.1, isn't it?
Yeah.
It's 0.1 lambda approximately. Do you agree with that? 0. Actually what? 0.9, isn't it? Anyway, we're gonna call it 0.1, just because I don't feel like fussing. So it's 0.1 lambda, correct?
It's negative.
What?
It's negative.
Yeah, negative. So now what we have to do is add a half wavelength to this. So you have to add 0.5 lambda, and that gives me 0.4 lambda, correct?
Yeah.
So that means I have to move down this line 0.4 lambda. And now, at this point, the actual input, the normalized input impedance is going to be 1 minus J, whatchamacallit, 1.4. Isn't the input impedance right here at this point? It's 1 minus J 1.4. Is that right?
Yeah.
Okay, now So what do I need to put in series with this? I have to put in an element that has a plus J 1.4 value. Now, that's an inductor. A normal inductor has an impedance of what? J omega L, correct? But if it's normalized, you would divide that impedance by Z naught, and that would be equal to 1.4. You all agree with me here? Yeah, J 1.4. We're gonna get rid of the J's in a second, but you're right. That means the value of L would be what? L would be equal to 1.4 times Z naught divided by omega, or 2 pi times 10 to the 9th. And what value of L is that gonna be? Z naught is 100, so
22.3 nanometers.
0.3 nanohenries. Anybody confirm that? That's 140 over 2, so that's 70 over pi times 10 to the 9. That looks right. 22.3 nanohenries, right? That's the way to do this impedance matching with actual elements. Now, I'm going to tell you, this is tricky at high frequencies. Remember I told you about that solder ball? I was at 1.4 gigahertz. The higher in frequency you are, the harder it is to do impedance matching with an element. And here's why. You say you need a capacitor of say 15 picofarad. A piece of wire with a little bend in it can easily have picofarads of capacitance at that frequency. It becomes very, very hard to get exact values for any components to do matching at high frequencies. You almost need tunable devices, and I had experience with this when we did a design project. It was a senior design project, and we took a CB radio and turned it into a ham radio. Well, that's high frequency engineering. You know, and we had to use plastic screwdrivers and all sorts of other things where our hands got near there, the frequency changed on a lot of this stuff, the oscillators. It was a nightmare. Now, the way you get around that is what we actually do, and I'm going to show you this now. Instead of using elements, capacitors and inductors, and sticking them in there, what we do is we stick pieces of pieces of transmission line in there. And here's the thing. Most of the transmission lines we deal with, they're not coax cables. They're really microstrips on circuit boards. Have you all seen Doroid board or anything like that? Do you know what I'm talking about? Well, most of the stuff you do as electrical engineers, well, a lot of the stuff you do, has to do with either very large scale integrated circuit designs or board designs. Do you know what FR4 board is, the green stuff? Or Doroid board? These are simply pieces, you got a piece of copper, an insulator, another piece of copper. Now, if I etch out, suppose I just I etch everything off, but I put a strip of just copper of a certain width on top, all right? Right below that, another strip of copper, only that width. I etch all the other copper off. I have a transmission line. But if I go ahead and I put a little valley or a void between that piece of copper and the rest of the copper on the board, now I have a transmission line. You can make transmission lines on those boards by delineating a pattern, masking it and delineating a pattern very easily, very exactly. And you can do this stuff, and it's amazing how accurate you can get and how this becomes almost a trivial thing to do this kind of stuff. So when I have a transmission line, let me show you something. Suppose we wanted to get that minus J 1.4, right? I want you to watch this. Well, if I want to hook a transmission line in series with this that has minus J 1.4, I'll show you what I mean. Here's my transmission line. Now I'm going to take another piece of transmission line and with a short circuit, and I want this thing to have Zn right here is minus J 1.4, and the characteristic impedance will be 50 ohms. So it'll be the same, or 100 ohms. It'll be the same as before. Follow me? So how do I get minus J 1.4? Well, I start with a short circuit. So this is going to be with a short circuit. Now listen, I start with a short circuit, right? What is ZL for a short circuit, anyone? what is the value of ZL, the actual impedance? Huh? It's 0, right? So the normalized value is 0, correct? Now when we have a Smith chart, and I'll draw one here. Well, how about if I draw a mini one here? When I look at this is 0.25 lambda, and this is 0. Where am I going to come in? Well, I'm going to come in right here. That's going to be my ZL, right? Now, I need the value of the input to be equal to, I want this value to be equal to Z in normalized to be equal to minus J 1.6, correct? That's what I need, right? I'm replacing that capacitor with this transmission line. Do you follow me? And I'm hooking it in series. So what's that going to be? Well, I started at 0, right? How far do I have to move? I'm looking only at this outer rim. Well, right here it would be equal to what? J 1.6, or J1 right here, right?
Yeah.
J1, I keep going down here. That's a full quarter wavelength, right? And then I keep going down and I need 1.6, so I'm going to go minus 1.6. So I go through to about where? Here, is that minus J 1.6 or about here, isn't it? Minus J 1.6. Take a look at that outer rim. Isn't this about?
Yeah, it's somewhere
Yeah,
around there.
right there, yeah.
All right, so now how far did I go? We'll just take a look. Draw a straight line through there. And what is the wavelengths towards generator here equal to? Say it again.
0.338.
338.
Can y'all see it? See what I'm talking about? This is 0.338 lambda. I started at 0 lambda, didn't I?
Yeah.
That means the length of this has to be L of this transmission line has to be 0.338 lambda. But then I get an exact match. And with the way techniques are, this connection will be perfect. You can do this easily. You can have 2 transmission lines, you can connect them like that. And then here, from here on, that Zn is equal to just Z0. It's matched. Do you follow me on this, class? So that's using a transmission line instead of an element. Do you follow me? Now, it doesn't have to be a short circuit, although I would advise you to always do it the short circuit. And the reason is the minute I make this an open circuit, we're going to do it with an open circuit. But the minute it's an open circuit, here and here, you're going to have a plus to ground potential, right? Now, when you're on the board, what that is something that causes an electric field that could easily, it could penetrate, it could corrupt a circuit next to it. It can actually be felt by the circuit. It's a near field electrical field. It's not propagating, and you know, have you ever done the thing where you rub a balloon on your head? And as you get near there, you can actually feel the static electricity. It's not a propagating field, but what you're really feeling is an electric field, all right? When the hairs of your arms stand up and stuff like this, because it's very close to the actual source where the charge is. Well, when you have a lot of devices electrically jammed in an area, anytime you have a plus to minus potential difference, that field can actually influence the circuits next to it, all right? And remember, that thing's oscillating at a high frequency, and it can corrupt it. That's what I'm saying. You're gonna hear about things called intermodulation distortion, and you're gonna hear about interharmonic distortion, you're gonna hear about all sorts of things, but one thing you're gonna also hear about is something called crosstalk. And in my EMC course, I get into it. Crosstalk is literally the voltages on one part of a circuit influencing voltages in another part. They're being felt on other parts of the circuit. And that's what you don't want. And that's why I never tell people to put an open circuit, always a short. But I'm gonna, just for completeness, we're gonna do the open circuit deal. If it is an open circuit here, well, what's the impedance of an open circuit?
Infinite.
It's infinite, right? When normalized, it's infinite. Infinity divided by anything finite is still infinite. So that means when you come into your Smith chart, you come in over here. All right, that's going to be your, if this transmission line is an open circuit, this would be your Z load right there. Now if I move from there to minus J 1.4, it's exactly a quarter wavelength less than the other one. Do you all see that? So it's shorter. Downside is It also has this open voltage here that can influence nearby elements, and it can really affect them badly. So remember that. That's how come I never ever tell people to use that unless there's an overwhelming reason for it that I can't think of right now. So I don't ever tell people to do that. But they do it sometimes when you're dealing just with transmission lines that are coax cables. Sometimes they'll do something like that. I hate that because it also means it's susceptible to stuff. That's a little antenna there. So it introduces a new form of EMC problem because now you can get signal coming in there too. All right, that's basically impedance matching using series elements. I'll give you a quiz now. And does everybody have a Smith chart, compass, and pencil? Yes. Does anybody have a second compass? I'll tell you what. Let's everybody spread out. Give it.